Hello student. In this session I will discuss about the isomerism in the coordination compound. Similar to the organic compound, in the coordination compound we also have two types of the isomerism. First is the structural isomerism and second one is the configurational isomerism that include the geometrical and optical that I will discuss in the next session. But in the present session I will only discuss about the structural isomerism of the coordination compound. In the structural isomerism we never take any reference of the space. We discuss the isomerism without any reference of the space. Okay, in today's session I will discuss only about the structural isomerism, means we are not discussing anything in the 3D, we are only discussing the thing which is happening in the 2D. So structural isomerism in the coordination compound divided into the several parts. The first part of the structural isomerism is the ionization isomerism. Look what we have. Suppose if we have any ion in the ionization sphere and similarly another ion in the ionization sphere. If we exchange these two anions from the ionization sphere to the coordination sphere, we have a new kind of the compound, and that compound formation is possible by the exchanging of the ligand. So this ionization isomerism is due to the exchange of the ligand between the coordination sphere and the ionization sphere. And if I dissolve this compound in the water, it gives the SO4 minus with the BaCl2 provide the white color of the BaSO4. But if we take the another isomer, as I told you, what we have to do, we have to exchange the SO4 minus with the Br. So what is the next isomer we have? CO NH3 whole 5 SO4 Br. If we dissolve this isomer number A, isomer number first, it gives the SO4 minus in the water. But if we dissolve the isomer number 2, it gives the bromine minus inside the water. Means by this kind of isomerism we have the different ions present in the water. Now the next isomerism is called hydrate isomerism. As we know, water can act as a ligand, as well as it can also act the water of crystallization. Whenever we have any water molecule outside the capital bracket, outside the coordination sphere, it works as the water of crystallization. But whenever this water molecule is present inside the coordination sphere, then it acts as a ligand. Suppose I have this compound. In this compound, 5 water molecules acting as a ligand and 1 water molecule act as a water of crystallization. Coordination number of the chromium plus 3 is the 6. So how many ligand we have? 5 ligand water and 1 ligand Cl. If I exchange this water molecule with the Cl, so what the next structure I have? I have Cr H2O whole 6 Cl3. Isomer number 1 provide the Cl minus in the water, 2 Cl minus in the water. With the AgNO3 it gives the 2 moles of the AgCl. But isomer number 2, it provides the 3 moles ion of the chlorine minus It reacts with the excess of the AgNO3 to give 3 moles of the AgCl2 with the concentrated H2SO4. When the isomer number 1 undergoes the hydration, it loses the 18 gram of the water molecule, but isomer number 2 never lose any mass. It never undergoes the dehydration. So this hydrate isomerism is due to the exchange of the water inside the coordination sphere and outside the coordination sphere. Inside the coordination sphere it acts as a ligand, but outside the coordination sphere it acts as a water of crystallization. Now check the next isomerism. It is called the linkage isomerism. Linkage isomerism is possible only in case of the ambidentate ligand. An ambidentate ligand has the 2 donor side. It can donate the electron either by the atom A, or it can donate the electron either by the any other atom B, like NO2. If we see the NO2 structure, double bond O negative and 1 lone pair. So it could be the nitrogen donating, it could be the oxygen donating. The first atom which we write always represent the donor atom. In this compound nitrogen is donating, but if I write this compound CO, O, N, O, NH3 whole 5 Cl2, this compound, this ligand become the oxygen donating. For this ligand, we in the UPSC naming we use N nitro or nitro N, or in this compound we use the nitro O. So linkage isomerism is only possible in case of the ambidentate ligand, which has the 2 donor side. Either it donate the electron pair by the atom number 1, or it donate the electron pair by the another atom number 2. Now next we have the coordination isomerism. In this one, cations and anions both are coordination pair. We have the cationic coordination pair, we also have the anionic coordination pair. And this isomerism arises due to the exchange of the ligands from the coordination pair, from the cationic coordination pair to the anionic coordination pair. Suppose if I exchange the Cl and NH3, next ligand, next compound can be NH3 whole 3 Cl plus 1 Cu Cl3 NH3 minus 1, or Pt Cl3 NH3 minus 1 Cu Cl NH3 whole 3 plus 1, and one more compound we have. Now you check in this one, isomer number 1, 2, 3 and 4, when we have all the chlorine here and now the NH3 here. These are related to each other as the coordination isomer. They are the coordinate, they show the coordinational isomerism with the each other. What is the specialty about the coordination isomerism? In this isomerism we require the cationic coordination pair as well as anionic coordination pair, and this isomerism is due to the exchange of the ligand from the cationic coordination pair to the anionic coordination pair. Now we have the polymerization isomerism. Although sometimes many books write it is not the real isomerism. What is the polymerization isomerism? We have a common empirical formula. If some compound show the chemical common empirical formula, then that isomerism comes under the category of the polymerization isomerism. Suppose if we write the N is equal to 1, then we have the isomer PT NH3 whole twice Cl2 1. But suppose if I write the N is equal to 2, then compound become PT NH3 whole twice Cl2 whole twice. Now you check this first and this second, they both have the same empirical formula. What are the possible structure of this compound? With the PT, you can write the 4NH3 plus 2 charge, another PT Cl4 minus 2 charge. Now one by one you can also exchange the ligand between the PT and Cl. What is the next possibility we have? PT NH3 whole thrice Cl plus 1 PT Cl3 NH3 whole 1. This is the compound we have. So if you see first and third, first and fourth, first and third polymerization isomerism, first and fourth polymerization isomerism, but second and third are obtained due to the exchange of the ligand between the cationic coordination pair and anionic coordination pair. So they are connected, they are related with each other by the coordination isomerism. Next we have the coordinational positional isomerism. This isomerism is only possible when we have the bridging ligand. Now you check this one. In the left part of the ligand, cobalt is connected with the 4NH3. In the right part of the ligand, cobalt is connected with the 4Cl-. This isomerism arises when we are exchanging the ligand from the one part of the compound to the another part of the compound, like first one is this. Second, if I write CO NH3 thrice Cl CO NH2 mu amido OH CO Cl3 NH3, we can exchange one more Cl, one more NH3, then these two compounds are related or has the relationship between each other, that is the coordinational positional isomerism. Next we have the ligand isomerism. What is the ligand isomerism? This isomerism only arises when ligand itself has any isomerism. Like first this one, this is called the 1, 2, 3. This is called the propene prop 1,2 diamine. But if, and it is the bidentate ligand, but if I write CH2 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 NH2 NH2, this become pro 1,3 diene. It is also the bidentate ligand. And now maybe the isomerism is not present in the compound, but isomerism is present in the ligand. So compound can be optical, compound can show isomerism due to the isomerism present in the ligand. Okay, so this kind of isomerism we only have when we have any isomerism in the ligands. Next and last one is the allogens. Allos means different, gonia means angle. You might heard about the temperature based paramagnetism. We have some compound, when we heated them, number of unpaired electron increases. Then on the cooling, the number of unpaired electron again decreases. How? Suppose we have any compound of the nickel at the low temperature. At the low temperature, this compound is the square planar and show the angle of the 90 degree. When we heat it at the high temperature, this compound become the tetrahedral, unpaired electron increases, and then we cooled this compound, then again at the low temperature it becomes the square planar. So this time we have the difference in the angle. Here the angle is the 90 degree and here is the angle is the 109 in the 28 minutes, and this process is also responsible for the temperature based paramagnetism of some compound. Thank you. In the next session I will discuss about the optical activity and geometrical activity present in the coordination compound. Thank you.